I don't know what we're doing.
Bro.
Sus. I don't know. What happened?
We are very pressed. You're probably wondering how we got here. Presenting Team HAMM for the ME2110 Spring 2020 Final Robot Design. This semester, we were tasked with 5 challenges to help Andy and the other toys from Toy Story. The challenges follow as launching the system, rescuing Buzz from the aliens, launching his rocket to infinity and beyond, returning the RC cars to the truck, and returning the toys to Andy's van. Pictured in the middle is the competition floor where all of the tasks must be completed. Task 1 is launching the system. The machine must move outside the start zone. Task 2 is rescuing Buzz, who is a wooden cube surrounded by aliens who cannot be moved outside of an 8-inch red ring. Task 3 is lifting a 6-inch rocket to a minimum of 42 inches above the competition floor with a maximum height of 100 inches. Task 4 is delivering 3 RC cars to the truck which matches the color of the start zone of the robot. Task 5 is delivering the toys to Andy's van, which is located on top of the middle beacon. Some of the largest design constraints we faced were regarding mechanical strength and timing. Adapting the code and the mechanics of the robot to fit within the 40 seconds we were given to complete all 5 tasks was challenging. Fitting the robot in the go-no-go gauge, a 1.5 foot by 1 foot by 2 foot box, also proved to be challenging. In addition to these challenges, limitations with the motors, as they were difficult to fit couplings on and adapt to our gear systems, came into play. Getting the cars into the beacon accurately without them falling off also became an issue. Too slow, and they won't reach it. Too quickly, and they'll fall out. Rescuing Buzz was also a challenge, as he was placed very close to the aliens, so it was very difficult to remove him without hitting them. To solve these design challenges efficiently, the design team constructed a house of quality. In the key customer requirements and engineering specifications were decided. Let's take a closer look. Engineering requirements are getting the highest competition score possible, making whatever device we create programmable by MyRio LabVIEW, making the device vertically extendable to complete placing the toys in the van and raising the rocket, and horizontally extendable to retrieve Buzz and to place the RC cars in the truck. Comparing those to our customer requirements, we have most notably passing the go-no-go gauge, making our device autonomous or able to run after one push of a button by itself, being able to launch the rocket and rescue Buzz, as these give the most independent points, and delivering the cars to the truck, as these give the most points when including egress. To satisfy our customer and engineering requirements, a specification sheet was compiled. Some of the most notable of these specifications are the limiting height and width and the limiting length. We chose the length to be 2 feet because we wanted our robot to egress and be able to roll over the aliens. This is shown in our horizontal wheel distance of greater than 11 inches. Under kinematics, we also added a minimum of 5 feet per second as a horizontal velocity to ensure our robot reached the centerpiece with enough time to complete all 5 tasks. To satisfy our customer requirement of autonomy, one of our specifications was that the robot must function only under a single input start. We also were constrained by a budget of $100 here included and time. We were only given 3 minutes to set up our robot and 40 seconds to complete the tasks. The design team also determined a list of functions the machine must do to complete the tasks. The first 3 functions are moving to the centerpiece, dodging the aliens, and returning Buzz to the start zone. From these functions, 4 potential solutions were developed. The next 4 functions are launching the rocket, detecting the truck, delivering the cars, and returning the toy to the van. From these functions, 4 potential solutions were also developed. For our first competition, only the first 4 functions were required to compete. To solve the movement to the centerpiece, we decided to use the 4 wheels powered by a motor design. To dodge the aliens, we decided to make the wheelbase wide enough to navigate around them. To return Buzz to the start zone, we chose to pull it back to the start zone after trapping it when the machine egressed, and we decided to launch the rocket using a cascading lift. This CAD model depicts the design we came up with to complete these tasks. Subsystems are labeled here. The drive subsystem is shown here. We used 2 large rear wheels to drive our machine and 2 smaller front wheels to guide it. To power the drive system, a large DC motor was connected to a cylindrical axle using laser-cut gears and plastic lathed motor couplings. This was one of the first things we changed in our iteration of this design. The cylindrical axle was difficult for the set screws to grip, so we traded it for a hex rod later. The Buzz retrieval trapdoor is shown here. A solenoid would release the MDF cage when the machine egressed over Buzz and pull it into the start zone to fully retrieve the block. For the rocket launch subsystem, the rocket was attached to the end of a 16-inch drawer slide using a mousetrap and a piece of MDF. The nose of the rocket was secured underneath a stopper to ensure the machine fit inside of the go, no-go gauge. A series of pulleys was used to raise the rocket in the 40-second time constraint. During our Competition 1 performance, we scored launch points in all 4 zones. We also consistently raised the rocket. Because of the uneven wood on the testing zones and the steepness of the track ramps, we were unable to carry Buzz back to the start zone at all. Also, due to the mechanics of our Trap Buzz trapdoor, one of the aliens was knocked over in the background, and we unfortunately lost points there. But overall, we totaled 223 points, putting us in 2nd place overall for our class. This proved to us that we needed to modify our Buzz design and our drivetrain design. This round also showed us how reliable our rocket launch system was, which allowed us to explore modifications for future iterations. For the second competition, all functions excluding returning the toys to the van were included. To solve the movement to the centerpiece, we decided to use the 4 wheels powered by a motor design. To dodge the aliens, we decided to make the wheelbase wide enough to navigate around them. To return Buzz to the start zone, we chose a pneumatically actuated pusher to launch Buzz back into the start zone. We decided to launch the rocket using a cascading lift, and we chose to use a ramp with a stopper to deliver the cars to the van. This CAD model depicts the design we came up with to complete these tasks. Subsystems are labeled here. Our drive system uses 1 motor that is connected to a series of gears that are used to turn the wheels. Unlike the previous design, the wheels have been moved inside of the machine's frame. This is to give us extra space to utilize on the top platform. We also used a hex rod instead of a cylindrical rod to grip the motor coupling. This helped the set screw attach to the system and turn the wheels more efficiently. Our Rescue Buzz subsystem is shown here before deployment. A clamp closes around the mousetrap trigger to hold it in place. A bolt was used to stop the clamp from opening, and a string is attached to hold it to the platform. The entire system was connected to the pneumatic actuator. When deployed, the actuator extends the mousetrap and pushes the bolt out of the clamp, allowing it to open and release the mousetrap. The mousetrap hits Buzz from between the aliens and into the start zone. The components were then raised up by the pneumatics to ensure it would clear the aliens. An IR sensor is used to detect when the machine is over Buzz. This is one of the largest changes we made from our previous design. By modifying it, we were able to safely rove over the aliens and avoid getting stuck on the ramp when trying to retrieve Buzz. Our rocket subsystem used the same cascading lift design as in our previous model. The RC car delivery subsystem utilized a Hot Wheels car track to place the cars in and held them in using a piece of MDF attached to a solenoid. The machine detected the centerpiece using a switch holder that dropped when the drawer slide extended. In the second competition, we disqualified 3 times due to computer code errors. The system that was set to indicate the machine had touched the centerpiece was unable to communicate with the motors, and therefore our machine kept driving and tipped over. The final round, we disconnected our motors and received launch points for moving our device only. For future designs, we would keep the design of our subsystems and the design of the frame the same, but spend more time ensuring the code worked. Should we have had a final competition, our projected score would have been 261, giving us a rank of, well, we'll never know. Thanks for watching, and thanks for a great semester.